DOE and Jefferson Labs, and he's been doing it for a long time. Great contributor to open source projects. Very, very smart guy. He's the guy that smart people go to help solve their problems. So please welcome David Bianco.
Thanks, Paul. So no pressure for me, right? So thanks, everyone. First of all, let's get this thing set there. That's a little bit better. So first of all, I know nothing about FedRAMP, so if you're in here for FedRAMP, sorry to disappoint you. So my name is David Bianco. I'm a security technologist, so I have one of these abstract business titles that no one knows what it really means. I'm a security technologist at Squirrel Data. Squirrel is a company that does linked data analysis for cybersecurity applications like incident response and hunting. That's what I'm going to be talking about today, but I'm not going to be talking about our Squirrel product. I'm actually talking about some open source software I wrote that I'm going to let you guys download from my GitHub and try to get your feet wet in linked data analysis. My job, though, at Squirrel is to kind of do some research into the ideas of threat intelligence, security analytics, how you can go deep into this big data and pull out the things that you really care about, and especially when it comes to incident hunting, like proactive detection of the threats that your automated detection did not find. I've spent about 15 years in the detection and response business. Paul apparently knows my bio better than I do, maybe. But yeah, I got started in the NSM portion at the Department of Energy in like 2004. But I've been doing incident detection and response even before then. I've had experience in government, research, educational, large corporations, you name it. So hopefully everyone in here will have something that they can relate to. I was a founding member of a Fortune 5 CERT. Sean was up here talking earlier about General Electric. I know Sean. I might or might not have founded GE CERT. I spent about 5 years helping to develop that organization from almost zero capability into something that could protect this giant entity that did business in over 100 countries around the world. At the end of it, we had something like 500 NSM sensors spread around the world, and we were collecting something like 4 terabytes of combination of NSM data and logs daily, not including the 5 or 6 petabytes of packet captures that we have. So I have experience doing incident detection and incident response at a very large scale. What I want to talk to you today is broken into 3 sections. In the first section, I want to discuss what it is that I mean when I talk about linked data. Once you have a little bit of understanding about linked data, we're going to talk about why you would like to use linked data and the linked data analysis techniques for proactive hunting on your network. And then I will start talking about the specific tool that I wrote to do some visualizations to kind of give you some big picture insights as a way of starting the hunt. So first of all, before I really get started, I'll ask a few questions. Anybody in here ever done work with linked data before? Raise your hands. I'm not seeing anybody. Anybody in here use Bro? Okay, all of you guys do work in linked data. You'll find that out very soon. All my stuff is based on Bro logs in this file. So if you have Bro sensors at your place of business, or if you're willing to take some packet captures and run them through Bro to generate the kind of Bro logs, you'll see that my tool that later on you can use the techniques that we talk about in here on your data. So first of all, let's talk about what is linked data. If you look at the Wikipedia page, they have this definition, which I think comes from the W3 consortium, a method of publishing structured data so it can be interlinked and become more useful through semantic queries. Technically, that's probably true, but I read that about 10 times before I could really figure out what it was trying to say. I'm a plain guy, so I kind of restate things in plain English. Linked data is just data that has connections to other pieces of data embedded in it. And I call two kinds, explicit links and implicit links. So implicit links are kind of inferred from the data. If you can see here, we have two messages. The first, who recognizes what this is? Just yell it out. Snort alert, that's right. What about this? It is a syslog for remote login through SSH. Unix, probably. Unix, definitely. So these two separate events probably occur on separate log files, probably even on separate hosts. But they have some relationships that are implicit in the data that they're providing you. So first of all, you can see, actually, this borders on an explicit relationship. They both name the same account. This first one says, it's a successful root logon alert. And this other one says, hey, I've accepted password logon for the root account. And they both mention the root user. So right there's one kind of link between those two. But you can see even better links, because if you look at this last part of the syslog, or the snort alert, actually encodes the source and destination IPs and ports. You can see the source IP is right here, another implicit link, and then the source port is here, and the destination has a little bit of a translation necessary, port 22, that snort doesn't really deal with protocols, it deals with IP ports. But the application, the SSH daemon, SSH is known to operate by default on port 22. So you have right there, depending on how you count them out, 3 or 4 different implicit links that show that these actually probably refer to the same event. Who remembers diagramming sentences on the blackboard? Yeah. So this is kind of the equivalent of doing that. We've taken the IP addresses and the accounts from the previous two log entries and kind of just drawn them visually. So here's the accounts, this is the account root, and here's the source host and the destination host. And we've connected them just with arrows that says, hey, this host connected here, they have a relationship, or which we call connected. And this account has a relationship with the destination, which says it logged into. Now, computer scientists, graph theory folks, you probably know, these are often referred to as nodes, and these are often referred to as edges. You'll hear me talking about those as well. Also, I'll probably call these things entities and relationships, but they mean the same things. So here we have just a visually, a little bit of a picture of what the relationship between those two log entries were. Now, explicit links are those which are actually stated in the log entries or the events. So we had some Bro users. Who can tell me, if you can read these, I have 3 Bro events here that all come from different log files. Who can tell me what kind of log file entry this first one is? I can't hear you. The conlog? No. The conlog is actually this one down here at the bottom. The first one here is the Bro files log. So the files log logs every file transfer that Bro observes over the network. And it has stuff. You don't have to know all these things yet, but it has things like the source and destination IP addresses that it saw, the protocol that it went over, in this case SMTP, so this is probably an email attachment. The MIME type that it observed, so this is saying it's C source code, and then it has an MD5 checksum value. And that's some other things here that we don't really have to care about too much. But this is the bro file log entry for this unique file here. Now, how about this next one? Any guesses? Yeah, this is the SMTP data for some transaction, and you can kind of see it has the host names and the email addresses and some of the header values, so something about phonetic software tag and some of the accepted headers and status codes and whatever. And then the third one, as we already talked about, is the con log. That's bro's connection log. It's similar to the same kind of information you get out of net flow, right? Who's talking to who, how much did they talk, and when and how long did they talk. So remember I said if you're using bro, you're already using linked data and you probably didn't even know it. Well, here's the links. In the con log, bro assigns every connection a unique identifier, just kind of a semi-random string there. And it references that unique identifier in other places, in all the other logs, because it's basically saying this file transfer was observed going over this connection. This file transfer was observed going over this SMTP transaction, and because this SMTP transaction went on the same connection. So you're basically showing all three of these things are related because they went over the same network connection. But there's even a little bit more. It's possible, for example, that you have more than one email going over the same network connection. You know, the two mail agents open a session, transfer a bunch of mail messages, and then shut it down. That doesn't necessarily mean that that file went with that email message. But bro also provides a unique identifier for every file that it transfers, or that it notices, I mean. And that unique identifier is also referenced in the other transaction logs. So this actually shows that not only did they all go over the same connection, they also went in the same transaction over that connection. So all three of these things are tightly tied together because of the explicit IDs that serve as links between the three. If you diagram this out, well, the first thing you might diagram is you might just say we have a connection entity, and we name it, here's the connection ID, that is related to the file transfer transaction that we saw. Here's the file transfer ID. And they're related by means of this contains relationship. So that you read this as connection whatever contains file transfer whatever. Now we can add some more details from the log entries that we just saw. So for example, we can add the hosts here. The source host for this connection is here, and it's related to the connection via the source relationship. So 194.7.248.153 is the source of connection, whatever. And similarly for the destination of that connection. Also, we can say the actual file object is related to the file transfer. So we can read this again with a contains. So file transfer contains file, hash value. Now, right here, we have a somewhat complete picture of the relationships between all of the entities in those three logs. It's a little bit clunky, though, because in order to relate the source and the destination, you always have to go through the connection, which might be what you want in a graph, like the technical term being a property graph. You might record a bunch of information about that specific connection on this connection node. but maybe you don't necessarily always care about the details of the connection. You're looking for the structure of the communication. The connection node would be getting in your way. So we can add what we call some transitive closure, which is basically saying we're adding the relationships directly between the entities, not necessarily always having to view the connection and file transfer transaction nodes, depending on what we're trying to do. So we can say, it's still based on those same three pieces of data in the verb logs, that this host connected to this host, it sent this file, and then this host received the file. Do you have any questions on that so far? Okay. So that, in a nutshell, is the idea behind linked data. You take row-oriented data like log files or events or of some sort, and you extract the entities, the IP addresses or the file hashes, or could also be user accounts, email addresses, whatever, MAC addresses, anything. And you put them in relationship to each other. And that's it. That's the easy definition of linked data. Now, why do we care about this? Why do we care about using linked data for hunting? So if you're using Bro, or if you're using something like Splunk or ELSA, or even if you're using just syslog and sending your logs into a flat file system, you're probably doing something similar to this, what I have on the slide. You're probably processing most of your events in a row-oriented fashion, and that is, here I have an example of the same kind of analysis of finding those links in the row data that we saw before. I have a specific file that I'm curious about. So in this case, it's an MP5 sum of the file, and I'm prepping for it in all my logs, and I find that the Bro files log has this. Here's the MP5 sum. And then I find that it has the connection ID that the connection occurred on. And so then I just rep the connection ID, and then I find the file log, and I find the connection log, and I find the SMTP log. And that's basically how a lot of people still pivot through things. They might not always use grep. They might be using something a little bit better. If you have some kind of log management solution, if you have Elasticsearch or some kind of bulk stack application, you might be searching with a nicer interface than just grep. But a lot of the times it actually still boils down to something like you have an indicator or a keyword that you want to find. You find all the occurrences of those, and then you manually have to pick out the other things that you're interested in, and then do another search to pivot through them. Which is fine, but it can get kind of confusing. I am not trying to say that row-oriented searching is bad. I'm saying that there's also another tool in your toolbox, and you use both of them depending on which one will get you the results you're looking for the quickest. So consider that you have, I'll just say you have Splunk or something like that. You do a search, and you get back a row, or a whole page full of rows of data. It's like a wall of text. Now, as an analyst, who in here has had this happen to them, where you have a row of text, and it takes you maybe 5 minutes or 10 minutes, if you're lucky, to figure out exactly what that means, all those things mean, yeah, right? That's pretty common, that's fine. But imagine if you could throw all that data into a tool that would give you a more visual representation of the same data. So here, you could actually, instead of having to see the wall of text, you could see a little bit more like a malicious email was sent to an email address which belongs to a user who logged into this victim computer and then also observed some HTTP command and control and some net flows out to another, potentially an exfiltration server. Now, both of these views can show the same information. They're showing it in a different way. If you're trying to figure out what's going on, which would you rather look at? all the individual rows, or a nice summary picture of how everything is related? Anybody prefer the rows? Don't be shy, I won't mock you. Okay, I'm not seeing any hands. So I'm going to assume, because it's in my own self-interest, that everyone prefers this. Yes. And I think it makes sense. That's not to say that all the row-oriented stuff is bad. There are certainly times when that's what we want. So the row-oriented analysis usually operates only on individual events. But there are a lot of tool sets out there. So you can take your pick from very expensive ones to very cheap ones and free ones, all with similar levels of scalability and responsiveness and performance and features. So that's the good part. It's a little bit hard to see the big picture from that wall of text. Like if you find some events and you've done all the work, it took you hours maybe, but you've done all the work to find the relevant events for your incident, and you've listed them all in a spreadsheet, and you hand it to your boss and say, I have analyzed the crap out of this incident, and here's what happened. And he's looking at it going, what? I mean, not to pick on the boss. I mean, the other analysts next to you would have the same comment. They would say, what? I don't know what you're talking about, all these events. They have to pay this cognitive deficit at first. They have to pay off the time to get their head inside all those events and try to figure out what they really mean, and it takes a while. So it's not necessarily the best way to communicate the big picture. Also, it's hard to pivot through those things because you can pivot one at a time. You find a log entry, you say, oh, this IP address is interesting, let's search for that IP address. Hey, this protocol that I was using is interesting, let's see if anyone else is using that same protocol. The file that I transferred was pretty cool. Let's see if I found that anywhere. And then now you need to go back 3 steps because you want to look at a different IP address and repeat that. It's possible to do, but it's really easy to lose track of your investigative leads and where you are. And there's just no real way of keeping track of all the things that you want to pivot through. Plus, you have to pivot through things like kind of one at a time. And you have to know what you want to pivot through. But on the other hand, this is really good when you need to do things like, I want to do a keyword search to find out where this occurred in my environment. I want to count how many of these events have occurred. Or, and this is a big use case for it, I think, is I need to actually furnish the proof that these things happened. So the log files and the event records are the best proof that you usually can find. So you still need to keep around all those raw lines of data, at least because after you've done all your other analysis, you need to be able to furnish the proof about what happened. On the other hand, now the linked data analysis, instead of operating on individual rows, typically when you're collecting this information over a long period of time, as you would if you were normally collecting it as part of your daily collection for your SOC, it tends to aggregate data. So every time you see the same IP address, it doesn't create a new record like it does with row-oriented techniques. It actually just adds the information to the existing IP address record. So there's probably only one IP address entity in your whole graph, or one for that IP address size. Also, when you interact with it, you can show it visually, so it's a lot easier to understand. You can give that graph on my previous slide to the person next to you in the next analyst seat, or to your boss, or to an auditor, or even law enforcement agents or anybody, and they can kind of visually see what's happening very quickly. It lessens the cognitive overhead that you need to get your head around what has been happening. And probably the biggest draw for me is that there have been literally decades of computer science research into how to do really cool things with graphs that mostly we are not using yet in our industry for cybersecurity. So, for example, we can search for specific patterns in graph. Like if we already know that there's a set of relationships between entities that we want to find, because we found it a lot in our previous incidents, we can search for those. That's kind of like the graph equivalent of a signature. We can also kind of identify important graph nodes by computing things like page rank or centrality of some sort, which basically just says which nodes are more important based on whatever kind of importance you're trying to find. So for example, if you have 50 nodes that are compromised by an attacker, and you want to know things like where are they spending the most of their time? It's like where are they downloading the tools to, or where are they aggregating all the stolen data to prior to sending it out? Maybe which ones these are their command and control points. You may be able to do something with like the page rank or centrality to find which of these nodes are the ones that they access most. Like in the connections that they make through this graph, which ones are the most important? Size those bigger on the visualization so that you can visually know these are the ones I need to go check out first. Another cool one as well is this idea of path finding. So given two nodes on a graph, how can you find if there is a valid path through the graph that connects those two nodes? I call this auto pivot plus because if you think of how you pivot through like Splunk, you pick a specific thing. I want to pivot off this IP address, and then you pivot off the host name, and then you pivot off the, I don't know, the user account name or whatever, but you have to choose those. On the other hand, now think of at a graph level, I have pie in the sky here, but I have like a lot of intel hits about suspicious email messages I've gotten. And I have a lot of alerts from my Snort IDS that say, I've seen this kind of malware beacons go out of the network. Now imagine if you could say, well, I have these 20 suspicious email messages, and I have these 300 beacon alerts. Find me if there's any paths between any one of the messages and the alerts. If there are, and that path is reasonably short, that might imply that there's a relationship between them. And you might find that that path actually will show you, well, the email message was to the user logged into the host had this DHCP address at this time, and that DHCP address was the source address of the beacon alert. And there you go, you told a little story. Then you probably still have to validate to make sure that that is a valid story. But if you've got a good graph model backing it up, chances are pretty good that you just figured out most of the kill chain of that event just by putting it in the graph and asking it to do an algorithm. So let's speak about that a little bit more. A typical IDS or SIM alert pretty much looks like this as a graph. It's just a couple of hosts and a source and a destination, and then an alert, whatever the alert is trying to tell you. I saw a beacon, or got a suspicious email message, someone logged in with too many login failures, whatever it is. If you're just sitting in front of the SIM console, you have a lot of work to do to figure out if this is a valid alert, or what you should do about it, or whatever. But consider how you can throw it into a graph and see, hey, here's the same 3 nodes in my alert, but now I can see it's connected to a login session where the user account was on this login session to the source IP address. And also the host name is attached there. So now you can identify the user and which exact host that user's maybe desktop, laptop, mobile is the source of that alert. Also on the destination, you can see, oh, it resolves to this certain host name. It was associated with a certain HTTP transaction which requested this URI, received this file, and used this user agent. You kind of have like instant context for the alert without having to go do more research about certain things. All right, so let's talk now about how we use all this linked data to do some visualizations that can give us the start of something, some hunting trips. kind of give us some situational awareness of what's going on with our network. Before I start talking about that, let me talk to you about the tools in my stack. First of all, if you want to go home, go back to your office and recreate these exactly, you can. I use, this is a public forum, I use the DARPA 99 challenge data, which is kind of, I should be ashamed of still using data sets from 1999, because I don't know about your networks, but my networks look a lot different than they did maybe 16 years ago. However, this is still one of the only fully open data sets that is available. We have in the security analytics world a big problem with the availability of large data sets that you can find really interesting things in. So you will still see the DARPA 99 challenge data a lot of places where we really shouldn't use it anymore. But in this case, the sort of things I'm doing, it doesn't matter as much. I'm not doing complicated analytics here. The next tool, oh my goodness, is Bro. The Bro Network Analysis Platform. You can get that at bro.org, it's open source. This third one here is my scripts, and you can get them from GitHub. You don't have to worry about all these URLs. I will post on my Twitter feed right after. I'll post a link to these slides. So I'll have my Twitter handle on the last slide, and you can follow me, and you'll get the slide URLs. So these are the scripts that I use to generate. The scripts that I use to generate the graphs that you're going to see. The fourth one here is this graph database called Grexter. It's just an in-memory graph database, very simple. You run it, you send data into it, it stores it, you can do stuff with it. And then when you exit Grexter, it usually goes away unless you configure it to run it to disk. So it's just a stand-in for some other larger, better, more capable database, which we don't usually need just for this. And then the Python APIs here that make this all work and talk to the graph database. And then finally, this open source tool called Gephi, which is a interactive graph explorer with most of the important computer science graph algorithms built in. A lot of interaction that you can do with the graph, not just show me a pretty picture, but also click on things, explore, expand, zoom, change the layout, compute all kinds of statistics for centralities or whatever. It's really a nice front end for working with graphs. So if you have all these things, you can actually take what I'm about to talk about home and do it either on the sample data that I have or on your own network data to a kind of a small scale. So basically what I do in my script is I take all of the Bro logs, I pick out like the first 4 or 5 types of logs that I think are the most useful. So connection logs, status logs, HTTP transactions, file transfers, that sort of thing. And what I did was I graphed them all and just threw them all together up on the visualization just to see what it would look like. All the different nodes are color-coded, so if you know what color codes are, it's not important for this one. You'll know what they are. So like blue, anywhere you see blue is an HTTP transaction. Anywhere you see yellow is a file transfer. There's all kinds of other like greens and things like that. Anytime you see red, for example, it's a host. I found that this kind of shows you a little bit of structure, and there's some obvious hubs of activity, but it's really confusing and it gets really messy. It didn't really tell me that much. So what I decided to do would be to filter out some of those nodes types and just start small. So first, I just said graph all the hosts. Now the layout algorithm here tends to associate hosts that are connected or related somehow together. So usually if things are somewhat close on the graph, they are somewhat close in some sort of relationship. And so that way you can start to see some of the interesting features. I also set the size of the nodes to reflect the number of times that it participated in a network connection. So the larger ones participated in more network connections than the smaller ones. And the same thing for the edges between them. the heavier weight edges participated in more connections. Is basically a count of the number of connections. And so you can kind of see some interesting things. Like up in the corner, you'll see these two big hosts connected by a big fat line, whereas almost everything else is really small. So what's that about? It's a little bit hard to figure out, though, what this thing is telling you, because all the hosts are colored the same. So what I did next was I did what in graph theory they call a partitioning graph. I set it into 3 categories, and I assigned each category a color. Row, if you configure it properly, will tell you when it knows which host is on your local network. So any of the hosts that are on the local network are colored green, and any of the ones on the internet are colored red. And if I didn't know which one they are, they're colored just light gray. Mostly that means they're probably on the internet also, but not always. So now we can see a little bit more, just by manipulating the graph, a little bit more of the story. We have an internal host here that's communicating a lot with the external host. There's a lot of connections. As a hunter, I think, find the big things first, get them out of the way. So probably start with those. So what I did to find more of the story was I figured if this was something that I really had a problem with, I might first think, oh, what kind of files are being transferred? Or are there any files being transferred? As it turns out, there were. I added the yellow file nodes to the graph, and I found that there's some really interesting relationships. So those same 2 hosts are right up here in the corner, and they kind of make what I call the dandelion. There's a lot of files being transferred between those 2 hosts. And there's some down here with the other hosts, but nowhere near the same magnitude. So what's going on? What are those files? All I had to do was zoom in on the graph. And I realized this is really super hard to read on the slide, but each one of these files actually has the MIME type. I wanted to know what types of files were being transferred. I didn't figure the file names would tell me much, nor the hashes, but the file MIME types at least would tell me generally what kinds. And if you look at those, most of those are images. Just a few HTML pages, but most of them are images. So that tells me this is probably all web traffic. The really thick connected to edge shows that the HTTP transactions were initiated by the internal host. And then all the files, mostly the files were sent back from the internet host, which is normal HTTP. You render an HTML page and you have a bunch of graphics in it. And then the directions on the arrows that connect up here, if you zoom in super close, they show the same direction that we expected. So that kind of tells me that this is most likely to be legitimate traffic. It's just something that happens to communicate to the internet a lot. And if you dig into it a little bit more outside the graph, I found that this was a Canon printer calling home to Canon for support updates. So the next thing I did was I said, fine, I just realized that I didn't care about any of that traffic. Let's filter it out and simplify my graph. What's left is a lot simpler. We don't really, I kept the same host, but I filtered out the files. We don't really have time for a full investigation of the entire data set. But if you think of the process is find the biggest thing, or maybe the most interesting thing. Sometimes they're not the same. Find that, figure out what it is. If it's something that you care about, then great, you found an instance, you can start your incident response process. If it's not something that you care about, you can filter that out of the graph and keep going. Find the next biggest thing or the next most interesting thing until you're down to a super simple graph. In theory, you would get to a plain graph, but no one ever has that kind of time. But as the longer that you go through that process, the more likely that whatever's left is suspicious. So that was host-based analysis. I'll leave you with a bonus single slide on user agents. So in HTTP transactions, all of the transactions have a user agent value associated with it that is supposed to name the software that created the HTTP request, right? If you think of most corporate environments, if anybody here is an educational institution, this probably won't be as good for you. Most corporate environments, they have standardized computing platforms. And so they usually have the same small set of web browsers that they support. You know, of course, everyone's going to support Internet Explorer or now maybe Edge. Probably Firefox and Chrome. There might be a few different versions of each. But you should expect that most of the legitimate web browsers show up a lot in the data. So what I did was I said all these green entries here are HTTP transactions, and in the middle of each cluster, kind of like the black hole at the center of the galaxy, is one user agent in brown. So really what you're seeing is a visual representation of how common all the user agents are in your environment. Where before, in the last one we said, you know, probably the largest ones are most suspicious, the user agents, that's actually the opposite probably. Unless you have a giant malware outbreak or something. The ones that are most common are probably the most legitimate. That's probably Internet Explorer, maybe Chrome or Firefox down here. But there's some smaller ones, like intermediate-sized ones, and then some really tiny ones that barely even show up on the graph. So the fewer times that you see them, the more likely they are to be some kind of individual malware, or maybe it's just some unwanted software that some person has on their one computer that you should probably take a look at. So in this case, you probably want to zero in on the small clusters, filter out the larger clusters. So I think I'm still finishing pretty much on time, right? So since I started a little bit late, can I have a few minutes for questions? Okay, any questions? Paul has one.
I think this is going to be huge for hunters. It's a way to really see what mobile looks like and then learn how to hunt and hunt. So that part I think is easy, but I think when you try to transition to hunting into protection, what would a rule look like a craft rule, what would that look like versus like a traditional like, work on this idea of order versus the craft part.
Right. So the question was, all the stuff I was talking about seems great for, you know, big picture visualizations and getting started on hunting and stuff, but you know, Paul wants to know at the end of a hunt, you found something maybe. How do you translate what you found into automated detection, like a graph signature, so that you don't have to keep doing the hunt over and over again? Which, by the way, if you ever read any of my writings, that's the main goal of hunting, is not to do the same hunt over and over again. So automate your successful hunt techniques so that you don't have to do them, and then you can do something else cooler the next time. So that's a great question. I think there are not very many examples yet of platforms or products that can turn graphs, explorations into signatures. There's beginnings of some of them, and certainly if you know a pattern, I think what the signature would basically be a pattern. And the pattern might be, show me when you have this kind of entity with this relationship to another entity that has this relationship to another entity. I don't know how many hops there might be, but you might have those, right? And it could be even more specific, so you could say, well, the first relationship has to have this certain characteristic, or the third entity in that hop has to be this kind of entity or something, right? I mean, you can apply a lot of logic to what the entities and relationships have to be and what their values and properties need to be in order to trigger that over. And you can do this in any number of graph databases right now as a search, but most security products haven't really actually incorporated graphs in there yet. So, with the exception, of course, of Squirrel Enterprise. So there are a few examples of how you actually, in a real world, can turn the results of graph exploration into an alert. But basically, basically, it's going to come down to what I just said. Some combination of entities and relationships and properties of those entities and relationships. There was one back here.
I had the same exact question.
Okay, yes.
Just to carry that conversation a bit further, do you think you could adapt something like OpenIOC as a format to create some new tags to provide signatures?
So the question is, could we adapt OpenIOC's XML format or something like it to be better suited for expressing those kind of graph patterns, right? Okay. Sure. Pick your standard. There's so many of them. That's the thing. I think, in general, to me, the graph techniques tend to be better at expressing signatures at the TTP level, tactics, techniques, and procedures. But most of the indicators that you would exchange with OpenIOC or Sticks and Taxi or whatever typically don't go that well to the TTP level. So I think there's a mismatch at the capabilities of what you could find in a graph versus what people are usually using those interchange formats to exchange. Maybe you could do it, but I don't really know. I certainly don't think anyone has done it yet.
Does encrypted traffic have any impact
Does encrypted traffic have any impact on this? So yeah, it has pretty much the same impact that it would have on your regular NSM situation in terms of what you can actually see in the transactions and stuff. But I think the graph has a little bit better edge there than regular IDS, because most of the other IDSs or SIMs are looking more at the flow itself, which is encrypted, so you don't really see that inside it. But with the graph, you can put it in context with all the other flows, and you can do kind of more traffic pattern analysis than you probably can do with some of the other tools.
You talk a lot about doing inputs. Have you any experiences kind of turning it around and paying attention to a web app and credentials being used in that web app?
Yeah, that's a great question. So the question was, I talk about hosts and everything in here, but what about monitoring applications and users' use of those applications? Certainly graph techniques could be adapted to that as well. The graph techniques don't really have to be network oriented. I chose those as my first test bed because first of all, I have an innocent background, so I'm more comfortable with the network side, but also because the Bro data model was already linked, and so I could take advantage of that when I was still starting this research project and trying to figure out what a good model should be for networks. So I thought, hey, Bro's been using this linked data model for 20 years. It must have something going for it, and it does. But certainly, if you, apologize again for talking about my own product so much, but when you come as a customer for Squirrel, that's one of the things we do. We model the things that matter to you. So you would model the applications and the users using those applications and do analytics based on those. You're not locked into a network model or an endpoint host model or anything like that. You can it definitely makes sense to apply graph techniques to all kinds of user activity, network activity, anything like that. One more question? Yes?
How heavy weighted is the graph now? I mean, really the graph, you may put something else logging or you have a terabyte of long data a day. How long does it take to build the graph?
So the question was, again, a terabyte of data a day. How long does it take to build a graph like this? First of all, if you have a terabyte of data a day, you should not be using my GitHub script. You should be giving me your business card, and I'll have our salesperson contact you. So how heavyweight is it, basically? This is kind of a prototyping tool. I wrote it for two reasons. One, as a quick prototyping tool for my own research in how I can use graph algorithms to do useful things, but also to give to people like yourself as a quick way, an easy way to get in and get your hands dirty with some graphs on your own security data. So given that, I would say that a large amount of data is going to crash the script and crash the little tiny graph database in that stack, right? It's certainly not intended to be an enterprise-grade solution. It's intended to be more of a, like, try it out and see if graph data is interesting to you. So I would not suggest that. Now, if you have like a couple hundred megs of data or something, you could definitely try that. To me, I get more value out of having a smaller data set of something interesting than just having a larger data set. So I would still advise, if you could, to kind of pare it down. Say, like, maybe you want to visualize an hour's worth of traffic out of one of your web servers, or maybe you're more interested in a little, the shop floor or manufacturing piece of your company's traffic or something, just to make it easy on yourself. You can work at larger data volumes with this stuff, but it will take a lot more resources and it'll act a lot slower because it's not really, enterprise ready. But if you just want to know what it's all about, try a small data set, you'll get quicker interactions and it'll be more effective for you. And then if it proves out, then you can look at a bigger solution, I think. I think now I'm going to stop because we're coming up on lunch, but I'm certainly here for the rest of the conference, so if you want to come introduce yourself, get a business card, leave a business card, I'll be happy to talk to you anytime. Thanks.